Our next speaker is Professor Matei Ciocarlie. Matei Ciocarlie is an assistant professor in Columbia University. His main interest is in reliable robotic performance in unstructured human environments, focusing on areas such as novel robotic hand designs and control, autonomous and human-in-the-loop mobile manipulation, as well as shared autonomy, teleoperation, and assistive robotics. Today he is going to give a talk on accurate contact localization with few wires.
All right, thank you for the introduction. Thank you all for being here. Very happy to have the chance to give this talk. Also very happy for the lot, I guess, scheduling to follow immediately after Rob's talk, because I think there are a lot of concepts that really tie in together very, very nicely. And in particular, right from the get-go, right, I'm interested in motor control, in motor learning, in manipulation as an extremely interesting case of it. And as a user of tactile sensors, initially when I started thinking about this, what do we want from tactile sensors to use them for manipulation? And we want, obviously, lots and lots of data, rich data. What exactly that means, I'll get into a little bit later. It can even get philosophical. Then we want coverage of curved surfaces, and Rob made that point beautifully, and I'm not even going to dwell on it anymore, but I agree, that's critical, we need that. And then finally, okay, it's great that we have so many sensors that are proven in the lab as a patch, but then we need to put them in robot hands and have them integrated into fingertips and palms and sort of everywhere in the hand, and hands are small, right? So integration is really, really difficult. So these are kind of my wish list, if you wish, my Christmas wish list from tactile sensors. And this is kind of one traditional way of doing it. To some degree, this is a straw man, so please, give me a little bit of latitude there. But kind of one way to do it is to come up with one taxel, and there are so many methods of doing that. Piezo this and piezo that, right? You come up with one taxel, maybe it's resistive, capacitive. You engineer it very, very well. Calibrate and you hide all the nonlinearities in your transduction method by your calibration, and then you've got this one beautiful engineered taxel that you then replicate. And Rob was talking about the importance of resolution. So you try to replicate it with high density and in a very regular fashion, so you kind of know where your sensors are. So then later you have this very dense and regular matrix of sensors, so you can localize your events. You know where your touch is happening. And then in Ed's talk at the very beginning, he talked about, for example, how that leads to a big wiring problem. And in general, if each of these taxels is individually at rest, you can imagine just how many wires that means. If you put them on this matrix on a PCB, rigid PCB, now you've got a rigid, flat sensor that you have to put in your hand, and there goes your ability to cover curved surfaces and edges, right? So once you take this and try to put it in the fingertip, that breaks down. So this approach doesn't lead to us having good coverage of curved surfaces, doesn't lead to easy integration, few wires, easy manufacturing of robot hands. What can we do differently? Well, how about this other approach, right? We live in this golden age of machine learning. So instead of, instead of these precisely engineered taxels with all the nonlinearities hidden away and then carefully replicated, just give me data, lots of data. Just give me something from the taxel. I don't care if it's not very good. I don't care if it's non-linear. I don't care if it's hard to model. Just give me the data. And we'll figure out what to do with the data later. But I care that these sensors, I can embed them in 3D and really get good solid coverage of curved fingertips, and makes it easy to build hands using these sensors. So give me this very rich data in a way that we will then do useful things with it. So let me make this concrete, and the two ways in which we realized this approach. So if you imagine that we have our sensor, and here I'm showing kind of a rectangular patch, but it doesn't have to be rectangular. So this is the area where I'm interested in detecting touch, and I'm embedding two terminals, And the only thing that I care about is that whenever I touch, so I have an indentation happening somewhere on my sensor, some signal between these two terminals is affected by the touch, by the strain in the material, and it changes. So this can be, for example, resistance between my two terminals, if this is piezo-resistive. It can be capacitance, if this is piezo-capacitive. But the general concept is there's some signal between these two terminals that changes when my sensor gets poked. Now imagine that instead of just two terminals giving me one pair, I have a bunch of terminals. And then what's really nice is that I can measure my signal between all pairs of terminals. And the number of pairs that I can measure my signal between is actually quadratic in the number of terminals. So here, just 4 terminals give me 6 signals, but it's quadratic, right? With 8 terminals, I think you get 60-something signals, so the number goes very fast. I get a very rich data set with very few terminals. So few wires, lots and lots of data. Now, of course, this is going to be very hard to model exactly how touching here affects each of these pairs. But the data hopefully will be there, as long as touching in one place affects as many of these pairs as possible. So touching here gives me a signal between all of these terminals. Alternatively, the other approach is let's not really do these terminals in pairs, but let's imagine that each of these is just an individual pressure sensor. Maybe the tactile barometers that Rob was presenting, which is actually what we use, and I'll get to that in the later part of my talk. So now I have these sensors that are all embedded in my fingertip, and touching somewhere hopefully affects as many of these sensors as possible. How exactly? Very difficult to model. But I don't need to model that analytically, just give me that data. So really, in a way, what we care about is touching in one place. We want it to affect as many of these signals as possible. So crosstalk, instead of trying to get rid of it, instead of treating it as a bug, we embrace it. Crosstalk really is our friend in this approach, and then we use it to get to the information that we care about. So let me focus on these 2 examples. This is really the kind of the essence of my talk today, examples of these 2 approaches implemented in actual sensors. And first, I'll talk about the version where we have terminals that we measure, and we measure signal between pairs of these terminals. And again, the nice thing about this is that the number of signals is quadratic in the number of terminals because we have all of these pairs. And also we have greater spatial reach in a way, right? Because if I have 2 terminals, touch anywhere between them and hopefully also to the side will affect the signal between them. And we actually built 2 implementations of this method using completely different underlying transduction mechanisms, which we think is nice because it shows generality. So this is the piezo-resistive approach. We have 4 terminals, and we measure the change in resistance between all pairs of terminals whenever you poke anywhere inside this sensor. This is actually the first one that we built. The second one, our terminals, half of them are photodiodes and half of them are LEDs. And we measure, obviously, how light goes from the LEDs to the photodiodes. We pair all LEDs with all photodiodes, and we measure all of those signals. Again, anywhere where you poke inside of the sensor. And the sensor itself, you cannot really tell in this image, but it is transparent PDMS, so that light can go from the emitters to the receptors. But the concept is the same. We have these pairs of terminals, and some signal changes as you poke the sensor, as you indent. So, okay, what do we do with all of those signals? So first, the concept is general, but here this shows the piezo-resistive version. We simply learn the mapping from signals to the variables that we care about. What are the variables that we care about? Again, that's a very deep question. What data do we want from our tactile sensors? And that can even, it gets philosophical at some point. But let's say, for example, from Rob's talk, that what we care about is to localize contact. So we want to know where contact happened. And we want to know that with as high spatial accuracy as possible. So we have this nice mechanism where the sensor is on a very, very precise planar stage. So we can move it around. So we can poke it, and we know exactly where we're poking it when we are collecting our training data. So then what we do, here is the piezoresistive sensor. We poke it at known regular locations. We collect all of the training data. Whenever we poke, we get our 6 signals, which is the change in resistance between all pairs of terminals. And we just simply want to learn the mapping from the 6 signals that we get to X and Y, which is the location of the indentation. How accurately can we do it? So these are the results that we got. This is, unfortunately, it's not deep learning. It's shallow learning, sorry to disappoint. But the results that we get is that we can localize touch with a median error of under a millimeter. And this is a sensor that is 16 by 10 millimeters, so 160 millimeters square. So this is the surface of our sensor blown up. And then this shows the error in our test. So these are the 100 test indentations. And for each test, the base of the arrow is where the indentation actually happened, and the tip is where we predicted it happened. And you can get a sense for the kind of errors that we get and the exact numbers. And again, aggregate over the entire surface of the sensor, and we get under a millimeter median error. This is with a 3 millimeter indentation in all cases. This is what this looks like in practice. So this is our sensor. Again, just 4 terminals, each of them with 1 wire. And then you go ahead and you poke. And this is, again, 16 by 10 millimeters blown up. So the kind of shaking that you see is really kind of the order of a millimeter or less once you get to a deep enough indentation that you can localize it. So this is what it looks like in practice. So here, the good side of this was that the localization is quite accurate, is under a millimeter. In a way, and this doesn't completely, it's a bit of an abuse of terminology, but if you can do 1 millimeter accuracy over 160 millimeters squared, it's in a way as if you had 160 individual taxons. And we're doing that with 4 wires. So that's the plus. The minuses of this, you might wonder, let me find the slide that actually shows the sensor, what's with these channels? So one thing that was difficult here was when we are embedding our terminals into the piezoresistive material. And by the way, a lot of work just goes into building this piezoresistive material. And the papers say, treat it like it's, oh, you know, it's manufacturing 101. It's not. There's an incredible amount of trial and error to just getting the piezoresistance and getting the sensitivity high. But then to just isolate the mechanical effects that when you're touching, just your electrode embedding into the PDMS, just you're going to have mechanical effects there, separating that from the resistance change. This is why these channels are here, so that we get the mechanical insertions far away from the actual sensor. That's a problem. Another problem that we found with the piezoresistive material is horrible hysteresis. It takes so long for the signal to get back to where it was. So we liked the accuracy, but the transduction method had all of those downsides. So instead, we went to a completely different transduction method. We decided to do optics instead. So this is the sensor where half of our terminals are LEDs and the other half are photodiodes. And now, what's nice about it is that if you look on the top, and it's just a cross-section where you have the LED on the right and the photodiode on the left, and light travels between them. What's nice is that light really takes many paths from the LED to the photodiode. Obviously, there's the direct path, but then there's also internal reflection of the surface, right? If the angle of incidence is right, then you get a lot of light that just stays inside the sensor, and eventually it gets to the photodiode. So then, as your indenter makes contact with the sensor, even just a very, very light touch, just the slightest of touches is enough to disturb the surface and to get rid of some of this internally reflected light. Then, as your sensor keeps going down, at some point you start blocking the direct path between the LED and the photodiode. So then, if you map, so this is the depth of the indentation, so how deep your indenter is going, and then just a raw the raw signal that we're getting from the photodiode. And this is what it looks like. You get two very nice, very distinct modes. Right here, you're just barely making contact. Right, this is 0, this is 1 millimeter. So you're just barely making contact, and you get this beautiful, strong signal when you're just disturbing the internal reflection. And then you keep going down, and eventually you start blocking the direct path, and you get another beautiful, beautiful signal. Then what we did is we looked at how thick the overall layer of PDMS, of transparent PDMS should be, and really tried to get that such that these two modes are continuous. It's right one after another, so we get as little of this linear regime in the middle as possible. So with that, once you do that, you get this beautiful, strong signal throughout quite a big range of indentation, right? So this is at 0, this is at 5 millimeters. And again, I mean, this curve, you can probably take the nonlinearity out of it, but this is when the indenter is poking right between the LED and the diode. When you're off to the side, I mean, light takes many, many paths through this. So this is hard to characterize analytically, hard to fit functions to, but we don't have to. Oh, and by the way, another thing that we did is, why is this really from the top? It looks completely black. That's because we also have light hitting the bottom of the sensor. But then what happens is we had the PDMS bonding with the plastic underneath, and then taking a few seconds to unbond whenever we let it go, which was showing up as horrible hysteresis again. So to get rid of that regime, the bottom is just covered in another layer of PDMS, which is just made opaque by this thing mixing carbon black in it. So we lose some of our signal, but then we also don't have the horrible hysteresis of light just hitting the bottom. So this is what one signal looks like from one LED to one diode. Again, here there's eight of each, so we have 64 signals in total. The sensor is also a little bit bigger. So then we take the same approach. We indent the sensor at very carefully controlled locations, and we learn the mapping. This time we have 64 signals, and because there's more data, and also because it's a lot more sensitive, we can afford to learn not just location, X and Y, but also the depth, how deep we are indenting, right? So we're quantifying both localization and depth error. So let's look at what the results look like. This is how well we are doing on depth. This is predicted depth versus real depth on two different locations on our sensor. And you can see that, and this is loading and then unloading. So you can see that we actually get that by sector. That's the ideal case. We tend to be pretty close to that. Then we look at, can we use this to actually classify touch versus no touch? Can we accurately detect that first initial touch? These are actually somewhat a little bit old results. We're doing a little bit better on that right now. But you can see that, for us to be really confident that we are being touched, we have to get somewhere closer to maybe one millimeter of indentation. So at about 2/3, 3/4 of a millimeter, we're getting pretty confident that yes, we can detect touch. And again, this is all over the sensor surface. And then finally, this is how well can we localize. And this is at various different indentation depths. The way to read these is the same. These are arrows, and this is the surface of the sensor, so 32 millimeters by 32 millimeters is the useful area, so about 900 millimeters squared. And then for each of these, the base of the arrow is the real in location, the tip is where we predicted the location would happen. This is at indentation depth 0.1 millimeters. So here we're barely making contact, and the localization obviously is not great. At 0.5 millimeter, we already get pretty good localization. And then at 2 millimeters, at 4 millimeters, the arrows more or less disappear. They're hard to see. Blown up like this.
What is that roughly in force?
We have the Instron data. Do you remember, Pedro, by heart, the indentation depth versus force? I want to say that 4 millimeters maybe is on the order of 6 newtons, something like that. 10 newtons? The paper has, we put it on an Instron and we have the exact plots, so the paper has that information, we can dig it up. And these are the numerical results. So actually, once we are at about 2 millimeter indentation depth, our localization error, the median, goes to under half a millimeter. Aggregated over the entire surface of the sensor, which is 900 meters squared. And then also for the depth, once we get reasonably deep, we can predict the indentation depth to actually better than a tenth of a millimeter. And this is what it looks like in practice. Now so the size of the circle shows is correlated with the indentation depth. The location of the circle, again, this is our sensor blown up, 30 millimeters, 32 millimeters by 32 millimeters. And this is what this looks like in practice. So now we can actually take a look side by side at these two methods. We have the piezo-resistive transduction and the piezo optics. This one is a little bit bigger. We get better localization accuracy. We get accurate depth here, which then we didn't get. So in a way, this transduction method is much better. No hysteresis. That one was really hysteretic, difficult to build. But still, there's just for all practical purposes, we've moved on from the piezo-resistive to the optics. But still, there was something nice about just having 4 wires, right? Because here, each terminal is a single wire, whereas here, we have the LEDs and the diodes. You need 2 wires for each of them. We have 16 individual sensors, so it's 32 wires. There was still something nice about that. But because of performance and ease of manufacturing, we have essentially moved on to this version. Okay, so now let's, so far we've built these planar patches for testing. We feel like there's nothing intrinsic in the method that prevents us from doing curved fingertips. Of course, you cannot really say that until you've proven it, but that's what we're very actively working on. However, a context in which we have already done this in 3D is when instead of having terminal pairs, you just have individual pressure sensors embedded in the material. So we've moved on to 3D. This is our hemispherical fingertip. It felt like a hemisphere is as good a shape as any to start with when you're demonstrating the concept. And the individual pressure sensors that are built in are the tactile, the MEMS barometer strain gauges that Rob was talking about in his work. Of course, then it begs the question, where do you put your sensors inside your 3D surface such that you get that beautiful crosstalk that you can then disambiguate? This is our first version that we just did based on intuition. This is, you can see how they're done. And the sensors on the side, they're also angled at, I think, what, 25 degrees? 20 degrees? It seemed like a reasonable thing to do. But then one contribution right now that we feel we presented here in this workshop is we actually also put together a finite element simulation of exactly that, because we want in the future to find this distribution of sensors in a more informed way than just by intuition. So are we getting the kind of crosstalk that we want? So here we are indenting the sensor along a line, along the symmetry line, and as we are indenting along the symmetry line, you can see the 5 signals that we get from the 5 sensors. The middle sensor is the one that gets the strongest response, but then the other 2 in pairs, you get a response from those as well. And then the finite element and the real data match really nicely, which gives us confidence that we will be able to use finite element. This is what we're actively doing to find a better distribution of sensors. But already here we have the crosstalk that we were hoping for. So then the same idea, let's indent in controlled fashion and collect the data for our learning algorithm. What does the controlled indentation look like in 3D? This is not us, this is previous work. this is our version of it. We don't have the background music, but our indenting machine acquired a couple of additional degrees of freedom so that it can actually indent in 3D. And so far, all the indentations that we've been doing have been normal to the surface of the sphere, but we wanna move away from that in the future. What do the results look like? I mean, it is a 3D sensor, but because we are only indenting on the surface, we can think of it still as, we can present the results in 2D. So we essentially mapped the surface of the sphere to a 2D grid to show these. And this is what the results look like. The numbers here they're dimensionless because they're just from the mapping of the sphere surface into 2D, but they're very close to millimeters. You can almost think of these as being millimeters. And here we can localize touch. In general, the accuracy is about 1.5 millimeters to maybe 2 millimeters. And you can see what our error distribution looks like. And again, what we like is that the simulated data and the real data look, if you squint enough, they look reasonably similar, which gives us confidence, again, that the simulation will inform how to build better sensors in the future. And then quickly to tie into Rob's talk from earlier, right? We have just five sensors, and this is maybe 250 millimeter square area. So you think then the simple thing is that each sensor gets about a 50 millimeter square area in which it dominates. So that's the kind of accuracy you should be getting. But this is telling us that thanks to crosstalk, there's more information there. And if you actually extract it, you can do higher precision accuracy. Rob did mention that doing super resolution will allow you to get higher precision. You can think of it as this as being super resolution, and this actually says that maybe the data actually is there. You can do things if you can extract as much as possible out of your raw sensor data. So let me start wrapping up. The dirty laundry. Just put this up front. How about multi-touch? What happens if you touch in multiple places? Can you do that? What if your indenter has different shapes? All of our indentations so far is hemispherical indenters. What about shear forces and other things? And my overall answer to all of these is that we're working on it. Improve your underlying data from the transduction method. You keep working on your learning algorithm to extract as much as possible. And for all of these, for some, I have high confidence that we're going to get them. Others, I guess we'll see. I also wanted to very briefly mention proprioception, which kind of feel that it's a badly overlooked sense in manipulation. And this is a hand that, oh, shut up. Anyway, this is a hand that has no tactile sensing whatsoever, but it's able to do nice, stable grasping in many cases because it has proprioception, so it has essentially torque sensing. All hands have joint position sensing, but this one also has joint torque sensing. So this is something we're very actively exploring and hoping to combine the work on proprioception with the work on tactile sensing. So, in conclusion, it's 3 sensors, but it's really just one paradigm, which is let's get rich signals, as rich as possible. We will use them. We have data-driven methods that we will apply after that. But what we care about is that we avoid the manufacturing methods for the tactile sensor that paint us into a corner when we want to build a new Thank you. Okay. So we have these implementations with terminal pairs, which is nice because you get lots of signals with few terminals, or with just individual sensors, which we've already done in 3D, and we get high localization accuracy, high depth accuracy. What we're very actively doing is we're taking this guy and moving to 3D. With these sensors, as I mentioned, we're using simulation to find a better way to localize the underlying sensors underneath. We're hoping to also get shear, and instead of this hemispherical dome, actually looking at fingertip shapes, and hopefully very, very soon building a sensorized hand. I cannot wait to have a hand that will have proprioception and will have these tactile sensors with very good, maybe not full coverage, but at least very good coverage. So with that, I just want to give a lot of credit to Pedro, who's sitting right there, and he's manning our poster, who really deserves a lion's share of the credit, and Sydney, who couldn't be here today for this work. And yeah, thank you.
Questions?
So yeah, you mentioned that one of the main motivations is reducing the number of cables. Have you looked at the effect on your optical one, just reducing the number of cables, to see how that affects resolution?
If we take sensors away,
Yeah.
we have. Do you want to take this, Pedro?
Yeah, so it's, we have done that, and we took away just the signals from the software side. So we use the same sensor, we only consider just some of the signals instead of all 64. And we discovered that both the number of emitters and receivers that you use affect the resolution, but also the distribution that you have on the edges affect, because you want to get like a homogeneous coverage of the surface that you're actively sensing. So you also want to have like a good distribution, and yeah, obviously the number of pairs that you do use affects the resolution.
Is it kind of linear, or is it not quite linear?
I don't think we've actually characterized that.
So qualitatively, it degrades gracefully. There isn't a steep drop-off at some point where it just falls off a cliff. It degrades pretty gracefully as you take sensors away, yeah.
Anecdotally, you guys had to have done like shears and torques. That messes stuff up, right?
We'll see. So, well, on the optical one, just the shape of it doesn't really allow that.
Yeah.
But once we get to 3D, we'll do that a lot. On this sensor, one thing that gives us hope is that the underlying tactile sensors, the parameters, actually will give you negative pressures.
Right.
If you're pushing such that you'll get negative pressure on one of them. So we think that that'll help. But
That's probably good data.
we don't have actual data.
One more, sorry. So you're doing machine learning or some other kind of big data processing. Do you ever? It seems like
Medium-sized data.
medium. Like, I agree with Rob. I love analytical algorithms. This seems like a perfect application of Cleaves function, right? You know the boundary conditions, figure out what's going on the inside. Have you guys thought about it that way?
Yeah, but once you think about the fact that this is complicated geometry, it's sensors kind of all over the place. And it's not, for the optical one, it's not just how the deformation in between them, it's, light will bounce off the walls and off the surface. Yeah, maybe you could. It's possible that you could. Let's say you have that model, but even then you have to invert it after you create it, right? So creating the model is only half the battle. I would say it's maybe just a little bit of the battle, because then you have to invert it.
Yeah. I'll send you some. We did some of the biotech, but it got all screwed up when we did torques.
Okay.
So in the interest of time, we need to finish the discussion section now. Thank you again.
Thank you.